Hey guys, Mr. McKinney here, just recording our last video in the Unit 9 series. So this is the 9.6 video series on exponential growth and decay. Now this is my second time trying to record these videos because I had myself muted the first time. So hopefully I have fixed that issue for this video. You guys have been learning about exponential growth and decay going all the way back to Algebra 1. So in Algebra 1, when you learned about exponential growth and decay, you learned this formula. Y equals a times b to the power of x. And basically what happens with exponential growth or decay is you multiply by the same thing every time as x increases. So as the value of x increases by 1, you're multiplying by the base one more time. So that's the factor, the growth factor, the decay factor, what you're multiplying by each time. And the initial value is what you had out front. So you guys have been working with the concept of exponential growth and decay for a really long time. Growth is when your a value, your b value is greater than 1. So if your base is greater than 1, then as you multiply by that number, it's going to get bigger and bigger and bigger. If it's decay, that means that your base is between 0 and 1. You can't have a negative base, because if you have a negative base, then your answer is bouncing positive, negative, positive, negative, positive, negative, and that doesn't make sense for an exponential growth problem. So your base has to be positive. It's either between 0 and 1 if it's decay, or it's greater than 1 if it's growth. Growth would look something like this. Decay is basically just flipped over the y-axis, and it would look something like this. Notice that in both cases, the values are always positive. They're either increasing always positive or decreasing always positive. Now, technically, you could make your a value be negative, and that would flip this over the x-axis. But usually, exponential growth and decay are going to be talking about real-world things, which aren't negative. It usually doesn't make sense. One other side note, you'll hear people talk about exponential growth all the time in the news. But usually they're not actually talking about exponential growth. They're just talking about something that grows fast. But if you look at the graph of x squared or x cubed or e to the x, they all kind of look the same at part of it. So quadratic, cubic, e to the x, they all look kind of similar when you're looking at this piece. So when you hear exponential growth on the news, take it with a grain of salt, because people use the word exponential without really meaning that it's exponential. Because again, exponential would mean that you're multiplying by the same thing every time, which is not happening in a quadratic or a cubic case. They all look like they're growing fast. Exponential grows the fastest. Okay, so the way that you're going to be presented with an exponential growth or decay problem in calculus is not with an explicit y equals formula. The way you would most likely see it in calculus is it would either say that y changes proportionally to the amount present, or the amount changes proportionally to the amount present. Realistically, though, you're probably going to see an equation like this. So you've got a differential equation that's equal to a constant times the amount. So notice that dy dt is based on y. So the rate of change depends on what the amount is at that time. Now, what we're going to do is we're going to use the concepts of differential equations to get our general solution here, and then we'll see how that connects to the concept of exponential growth or decay. So when you see an equation like this on the AP exam, in your brain that needs to trigger exponential growth or decay. And if you remember that, you don't need to show all these steps that I'm about to show you. So we'd separate the variables first. Dy over y equals k dt. Multiply by dt, divide by y. Integrate both sides. So I'd get ln, absolute value of y, equals integral of k dt. So the integral of a constant, I could pull that out front. So then it's the integral of 1 dt. So the integral of 1 is t. So this would be kt plus my constant. Now, I want to solve for y, so I want to get this expression from the logarithmic version to the exponential version. So I can do that by taking this side and making it the exponent with a base of e. So e to the kt plus c. Now, e to the anything, it doesn't matter if the exponent's positive or negative, e to something, if your base is positive, then this value is positive. If you think about the graph of an exponential, the graph of an exponential never crosses the x-axis. So the graph of an exponential is always positive. So I don't need this absolute value. Y is already going to be positive, so we don't need to worry about that. All right, now using properties of exponents, we can rewrite this one as e to the kt times e to the c. And then instead of calling it e to the c, c is just some constant, so e to the c is just some constant. So I'm going to call that new constant c1. Technically, you can still just call it c, but I think that's confusing for some of you guys. Then I'm just going to move that c1 in front. And then we're going to think about when time is 0. So at t equals 0, this piece would be 1. So at t equals 0, y equals c1. Now a common way to say the amount, like the y value when t is 0, is to say it's called y naught. So when t is 0, I'm going to call this thing y naught, which means that my equation is really just y equals y naught e to the kt. And this is the equation that we know and love from Algebra 1. Y equals a b to the power of x. Now it looks a little bit different in calculus. Instead of b, we have e to the k, but that is essentially our b. Instead of y naught, we had a back in Algebra 1, and then we just changed the variable since we had t here instead of x. But it could have worked the same way. Now notice that the k value in this original differential equation is the same k that shows up in this exponential growth formula. Now, if you memorize that this differential equation means exponential growth, you don't have to show all these steps. You can just go straight from, okay, I have an equation that models exponential growth, to, okay, well that means that we would have an exponential growth equation. So if you recognize this on the AP exam, you don't need to show all these steps. You can jump to here to start working it out. Now the rest of this video is just going through 3 practice problems. There's a note sheet that should be posted next to the videos. I would download that so you don't have to copy down all the word problems. So download it, print it out, and then there will be space to work these out. Each of these problems is a little bit different. There's different values that they can give you, and depending on what they give you, you're going to work it out slightly differently. So first one, the weight of a population of coronavirus is given by a differentiable function y, where y of t is measured in attograms and t is measured in days. The weight of the virus population increases according to this equation. So right here, that's what triggers that this is an exponential growth problem. It's telling me that k is a constant. At time t equals 0, the weight of the virus population is 130 attograms, and it's increasing at a rate of 26 attograms per day. So it gave me 2 pieces of information when time was 0. And it's asking me to find y, so the particular solution, basically. So let's give ourselves a little bit more space to work with here. So let's think about what we're given and what we know. So we have 2 equations that we're going to be working with. dy dt equals, not kt, ky, and y equals y naught e to the kt. We're trying to find y of t, so we're trying to find this equation. Now let's see what they gave us. So they said when t was 0, y was 130. Since it's when t is 0, that's telling me y naught, so I already know that part. And then it's saying the rate is dy dt, so it's telling me that dy dt is equal to 26. So I'm trying to get this equation, y equals, I already know that y naught is 130. So now I just need to figure out k, and then I will have my equation and I'll be done. They gave me a rate and they gave me an amount at the same time. It was time equals 0. So I can plug these 2 values in here. I have a rate, and then I have k times an amount, so I can solve for k. 26 over 130, which would be 1/5. So then over here, I can say y equals 130 e to the 1/5 t. And that's it. Now, like I said, each of these problems is going to be a little bit different, but the main thing is if you have this equation, you know it's really exponential growth. Or if it tells you that the rate of change is proportional to the amount present, that tells you it's exponential growth or decay. Okay. Looking at this next one, an isotope of kyber crystal has a half-life that can be modeled by dy dt equals negative 0.0077 y, where t is measured in years, and we're trying to find the half-life. So again, this question is pretty different from the last one, but we're using the same main idea. So we've got dy dt equals a constant times y. In this case, my constant is negative 0.0077. It's asking me to find the half-life. That's a concept that you should have covered in a previous course. Half-life is the time to decay to half of the original amount. Now, we don't have the original amount, so it's going to be hard to figure out when we have half of that. But it's true whether we start with 100 grams going to 50 grams, or starting with 1 gram going to half a gram, or starting with 1,000 grams going to 500 grams. No matter what, the half-life is the same. It always takes the same amount of time to get to half of what you started with. So we want to know, like, t is what when y is equal to 1/2 of y naught. That's what we're trying to solve. Now, I recognize that this is an exponential growth problem, so I can just start with the formula for exponential growth. Y equals y naught e to the kt. And I already have my k value, so I can plug that in. Negative 0.0077 t. Notice that this is k times y, but in this formula it's k times t. So k times y here, k times t here. Now, I don't know what y is, but I know that it's half of y naught. And now I can divide both sides by y naught to get rid of that. So now I just need to solve for t. To get it out of the exponential, I'm going to use a log. So I'm going to say negative 0.0077t equals ln of 1/2. Then I'm going to divide both sides by negative 0.0077. I'm going to do all that on my calculator. So I'm just going to type ln of 1/2 divided by negative 0.0077 on my calculator. And when I round correctly, I should get 90.019 years. All right, we've got one more problem, but I've only got like 2 minutes left, so I don't want to try to rush through it. And I'm also going to show you guys a calculator trick. So we'll pick up on that problem in the next video. Hope this was helpful. Have a great day.